Okay, welcome back. Today we're going to be talking about basically bringing together your reading from Chapter 3, The Laws of Light, which I have expected that you have at least dug into for the most part. This is a great part of the class, is tying what's in the textbook ahead of time into what's coming into the lecture. So Laws of Light will be a big part of this discussion today, as well as Chapter 4 from Solar Energy Conversion Systems. I want you to get reading into that as well. That's going to be the physics of light, heat, and work. These are going to be those fundamental topics that really set everything up for solar energy. I mean, here's the deal. Nobody out there is really taught solar energy from kind of its fundamentals. Nobody has a background in solar energy except you who are taking this class. You're really getting that foundation point, which is why we go through fundamentals. We really need to get that established from the ground up, which will set you apart from your peers. Okay, you have homework 1 due as a group coming up this, not this Thursday, but the following Thursday. It should be February 4th this year in the spring. And a reminder that those homeworks are due as your CATME group, and you are required to use the LaTeX template for the homework. There's actually specifically a homework template download in the DSEC, the DSESC website for the class. Okay, so go out there, work with your teams. You will be having more surveys with your teams to evaluate them and to try to grow your team into a stronger position so that by the time you're working towards your final projects, you have a really strong team who works together and that you can rely on. All right, thanks so much. Let's keep going. So one of the things that I wanted to bring to your attention is there are parts of this book that you can jump to the back of to get some kind of foreshadowing, some idea of where we're going. So I'm going to look at some diagrams of a photovoltaic system viewed kind of schematically in a thermodynamic sense as an energy conversion device. That's ECD. So you'll see here that I'm beginning to use what is in the reading of Chapter 3, the tool to diagram light. So where I have the sun emitting light, I've got that curved line to describe shortwave irradiation or irradiance that is input into the photovoltaic device. I've got a straight line, straight arrow, and I've got a little grounding look right here. This little grounding arrow look is the light being absorbed by the photovoltaic device. Okay. Then I've got boundaries around the system. The system is clearly an open system. There's both energy and mass flowing in and out of the system. The mass flow largely being electrons in this case. And then I've got optical losses, shortwave optical losses that we'll discuss much later in the class, as well as thermal losses. And it's those thermal losses that are partly covered today, where we're going to be talking about thermal losses that are due to long wave radiation. That would be light that is not visible to the human eye, and it's not the light that's coming from the sun, at least not in the density that we would expect. It's a light that might be emitted by everything glowing, including the clouds and the buildings and photovoltaic devices. So take a look at that. You're more than welcome to look into the back of the book. And then I'm going to bring up next a similar diagram, really similar diagram. And you see that I've got, again, my light source, my energy source is going to be the sun, where I have shortwave radiation that comes into a solar thermal panel. It's absorbed right there. There's my little grounding arrow of light being absorbed using the technique of diagramming light. Very important for this first homework. And then I've again have a diagram of thermal losses, which are inclusive of long wave radiation losses, because all hot things glow. So I advise you to take a look at those and to kind of understand schematically what's happening inside of this and how am I using this tool of diagramming light in the class. It's very useful, very effective. I'd like you to do more of it when you're actually kind of conceptualizing the way that solar energy conversion systems work. All right? Okay. So, starting with Chapter 3, we call this the laws of light. And the idea is that there's some basic fundamentals ideas that set up our knowledge for radiative transfer. Radiative transfer being the transfer of photons from one surface to another surface. And how does that light actually transfer? Now, in this class, we're much more specific and at the same time much more flexible about what we call light. Light in this case is really a large group of photons that effectively all electromagnetic radiation that in particular those shortwave and longwave bands that we're going to come up on in our reading in chapters 3 and chapters 4. So we've left the realm of, say, classic mechanical engineering class where radiative transfer is only talking about a long-wave body like a hot engine glowing with some amount of radiation. This is really talking about everything glows. So let's set things up. When I have light across any wavelength coupling with matter, that is technically optics. Okay, so optics is the coupling, the marriage of light and matter. And for us, light is we think of it as a pumping system, where light is an energetic influx that will ultimately pump up the energy of our systems in really creative ways. This is not conventional to what you normally thought of, but it works very well inside of the world of optics, say inside of lasers, where we do think of energetically pumping something up. We're just extending that idea of pumping into a whole host of applications for light. So optics, the word optics, very specific language, meaning the coupling of light to matter. So if I were to use my tool of diagramming light, I have two surfaces that are going to be interacting with each other. The surface of the sun, the external surface of the sun, very hot, and the surface of, say, my solar collector, whether that be a photovoltaic panel or a solar hot water panel or maybe even the wall of a building, right? Could be a tree. I'm going to use my tool of diagramming light. I'm going to diagram the sun emitting light. It's going to be emitting shortwave light by a straight arrow. And that light is then going to be absorbed. It's shortwave light that is absorbed. And when that light is absorbed into my system, let's draw a boundary around the system. When that light is absorbed, it pumps up the energy of the system in interesting ways, pumping up the energy of the system, really, and then allowing energy to leak out of the system through, say, long wave radiative transfer. But the interesting thing here is that inside of the world of thermodynamics or just energy conversion devices, we actually see a lot of discussion of heat pumps versus heat engines, like heat pumps where energy has to be input into the system to move energy to a higher state or to move energy from cold to hot, technically, right? Versus a heat engine, which would be a cascade of energy from a high energy down to a low energy state. In the case of solar systems, we actually couple those together. We couple a heat pump together with our heat engine. So the heat pump is that sun solar radiation that is flux being absorbed into my solar panel, just like a microwave is going to be a flux of light, microwave light, going into your cup of soup. You're going to pump that energy up, and then that energy can then be used as a cascade down in the case of electrons, in the case of hot water in a solar hot water panel. It's great solar. So coupling together of light and matter, added on top of that, the coupling together of systems, of us coupling a heat pump to a heat engine to do some really amazing energy transfer and energy conversion. A lot of exciting stuff. So you'll hear me talking about pumping things up. You'll hear about heat pumps and heat engines in Chapter 3, and that's the direction that we're going. So again, a lot of this stuff is summarizing what's written in Chapter 3, and I really expect you to have read that material and taken notes as you went on. Right, so the sun, right, and the sun is a big resource system. The resulting photons, the light that are emerging from the surface of that sun, that's a flow of light, which is really a current of light, and it's effectively a work current. This is useful energy. Shortwave light is incredibly useful energy. So we have a steady state condition on on most, say, sunny days. We're just making an assumption of steady state, but we know that light is a work current, a current of energy that does useful work to affect three different responses. Now, the first response, we're going to just tie into that idea that's solar as photovoltaics, or the direct conversion of light to electricity. Solar energy, shortwave light, this goes way beyond the visible. Infrared light, UV light, and visible light are all a part of the shortwave band. They can elicit in certain materials an electronic response, meaning I can lift up, pump up the electronic state of a system from a low energy state electron to a high energy state electron, and then I can let that electron leave the system through say a conductive wiring, and now my circuit can do work that is electronic. So we would call this whole study, the underlying kind of process, an optoelectronic process. I mean, we know optoelectronics are out there as a standard part of material science and electrical engineering, but we're talking about light matter interaction. That is the light matter interaction that elicits an electronic response. That's optoelectronic. You run that heat pumping system in reverse, and effectively you have an LED light, right? Okay, second thing that can happen is a caloric response. This is what you would have thought of as a thermal response, only thermal responses don't really capture everything because, of course, I can have light matter interactions that raise the temperature of an asphalt parking lot. I can that raise the temperature of a brick wall. That's a caloric response. At the same time, that light can be absorbed and can cause a phase change of water, right? Going from liquid water to vapor. The vapor-liquid equilibrium can be induced with a light matter interaction that has a caloric response. So we know we have a sensible heat change where the temperature of something changes, and we have latent heat change where the phase changes, and this is both encompassed in caloric. So we've actually needed to create a new term that is in parallel with optoelectronic, just to be useful for the fundamentals of solar energy conversion systems, and that would be optocaloric. So you're going to find optoelectronic discussions as well as optocaloric. Keep an eye out. Optocaloric is unique to this framework of study at Penn State. This is our school of thought that we've established over the last 8-9 years, and so keep a note of that as I discuss it in class or in my writings or in video lectures. So the third response, you know very well, it's an electrochemical response, or a photoelectrochemical response, we would call it, and that's going to be the same responses that you have when you look at light that is absorbed by the rods and the cones in your eyes. Those wavelengths of light have a very specifically tuned absorption that generate an electrochemical change in those absorbing species. Same thing in the photosystem 1 and photosystem 2 of photosynthetic processes in all of our primary productivity in leaves and plants and the like. That is a photoelectrochemical response. Third classic photoelectrochemical response is the cholesterol in your skin. So all of our skin contains, within the depths of our skin, contains a type of cholesterol that when absorbing ultraviolet light is then converted into vitamin D. So vitamin D conversion from cholesterol to vitamin D, that is a photoelectrochemical response. Fascinating stuff. But so the sun and the resulting flow of light, that work current, they can do three classes of really useful conversions that we will describe in this class. An electronic conversion, that would be called an optoelectronic process. A caloric conversion, that would be called an optocaloric process. Again, opto is light matter interactions. Caloric is both sensible and latent heat changes. And then electrochemical, which would be photoelectrochemical processes, ubiquitous in our Earth systems for primary food productivity and for processing information of light. Great stuff. Solar energy conversion systems. are fundamentally coupled to light. And the interesting thing here is that, again, if we look closely, we can really break down many solar energy conversion systems based on some key components, some key parts, subsystems, one might say. Each solar energy conversion system is ultimately going to be composed of an aperture. That would be the opening that allows light in, and an aperture does not actually have to be a physical material. An aperture might just be a hole in the wall, a hole in a cave, an opening in a doorway. That is an aperture. It's the opening that allows light in. It becomes much more important once we start thinking in terms of concentration of light. But for now, just think of the aperture as the opening where light is allowed in. The receiver is going to be that opaque absorber. Opaque meaning it's going to absorb light. It's not going to reflect light. That converts the sun and other forms of energy, right? The converts the light from the sun to other forms of energy. So a receiver is really that absorbing thing. Your eye, the rods and cones in your eyes are receivers. The lens in your eye is an aperture, right? In a photovoltaic panel, the glass and the frame on top of the photovoltaic might be the aperture. The receiver is actually the functional silicon or cadmium telluride absorbing materials. That would be your receiver. So there's an interesting dialogue between the aperture and the receiver. We could also say, going back to the aperture, that the aperture could be a mirror, right? In many of our concentrating systems, the aperture is a reflective surface that helps to allow light in and redirect it to the receiver. An aperture might be the ground, in fact, that also reflects light into a receiver. Sometimes in solar energy conversion systems, not always, there will be a storage subsystem because, hey, sunlight is intermittent. So I could have a battery storage system, I could have a water thermal storage system, I could have a sugar storage system. So in photosynthesis, the whole point of the aperture receiver system is to generate to run photosynthesis systems to ultimately generate sugars, where sugars are your storage. The distribution mechanism is internal to the system, and it's functionally the way that mass and energy are moved around the system and in and out of the system. So we always will have distribution mechanisms, whether that distribution mechanism be a wire circuit connected to a photovoltaic panel or a fluid channel for solar hot water systems, or a distribution mechanism maybe just the HVAC system in a building. So your buildings around you are all aperture receiver systems with storage of large masses of air, and the distribution mechanism might be that internal ventilation system. And control mechanisms are basically the way that we turn and allow the systems to adapt to intermittent signals and seasonal changes from the sun. So everything is going to have some sort of control mechanism. Even when we design our porches, the patios that are facing south in our system, that roof, that little awning that extends out to block the sun during summer months, is a control mechanism. It's a shading mechanism that actually works effectively to not allow really intense sunlight to go into your front room behind the patio. Whereas during the wintertime, the sun is low in the sky and the sun just pours on in. So let's look at a couple of examples of this where we might explain some of these aperture receiver storage distribution mechanism and control mechanism. Now, not everything is going to have a storage system, but almost everything has an aperture receiver distribution and control mechanism. And I like to do this so that we can fundamentally analyze everything that we're looking at and see how it functions, how a system functions as a solar energy conversion system. So here we have a series of pictures that comes from one of my online courses for graduate students. This is a part of the REST program, Renewable Energy and Sustainability Systems, for the solar option that I lead. This is EME 810, Solar Resource Assessment and Economics. very closely aligned with a lot of the materials in EGEE 437 that you're taking right now. So let's look at the upper right hand, or the upper left hand, where you're seeing a car park with photovoltaic panels that are shading things. Okay. What you're seeing is a lot of different solar energy conversion systems. So first and foremost, I'm not going to go to the photovoltaic panel. I'm going to go to this black top surface that you're seeing in here that is clearly a light absorber. It is going to be where the aperture might be the airspace above the black parking lot surface, but that's clearly a receiver. The distribution mechanism is the way that thermal energy is conducted throughout the pavement. Not much of a control mechanism that we're seeing in here. But certainly this car is going to be a solar energy conversion system. It's going to be one that captures optocaloric processes. That's light matter interactions for caloric processes. And then, of course, we have the photovoltaic panels, which are going to be an optoelectronic process and an optocaloric process. As long as you know that both things are happening. Light is being absorbed in a PV panel to generate electrons, but at the same time, and not necessarily wanted, light is being absorbed. Shortwave light is being absorbed, creating a caloric response. We have an optocaloric process going on, heating up those panels at the same time, which is really interesting because photovoltaic panels actually don't like the heat. They perform better in cold weather. So, interesting quirk there. Here, of course, in the center top is Ryoanji. This is the Zen rock garden that I've talked about before. You're looking at an aperture of the airspace above here. You're looking at an aperture reflected surface of these rocks. There's no actual visible receiver for the system other than the room that might be off to the side, to the north of this, where people are sitting and their visual light that is coming in is being received by their eyes, or maybe there might be some thermal gains inside of that room. Storage mechanism, of course, is going to be all of the air that is captured in here and maintained cool. There's a control mechanism, oddly enough, is partially tied to this wall and partially tied to the opening and closing of the door that you have next to there. On the upper right, you're seeing Ilek Diaz right here. Ilek is demonstrating his Liter of Light project, nonprofit. There is the 1 liter bottle. That is just containing water and a little bit of chlorine. The chlorine does nothing but keep the green stuff from growing inside of the bottle. And it's allowing light, right, effectively shortwave light, to be absorbed by this gentleman's eyes and by Ilek's eyes, right? And if I were diagramming light, you'll notice that I have a curved arrow going on here. So I always have an emitted source as a curved arrow coming out of here. Shortwave light that the receivers are people's eyes going on here. The control mechanism is a bit of the internal reflection that's going on inside of the bottle to allow light to diffuse. Down in the lower left, you have a solar hot water system, standard system, where the opening is the aperture. The tubes inside of here are painted black, and they become the receivers. The panel is connected into a tubing system down to a hot tub or a tank of water, and that, of course, is your storage device. And there's usually a valve systems and flow for distribution and control mechanisms. This lower right image is going to be the Building 101 in the Philadelphia Navy Yard, where a lot of our energy efficient buildings research started several years back. You're seeing a receiver as a tree. I'm going to point that out. You're also seeing a receiver as a building. The apertures are going to be these nice little windows for light going into the building, but this is also a brick building, so that brick surface is also its own receiver. It starts to show you how very complicated solar energy conversion systems are, and it should also tell you that there's just about everything out there acting in some way in connection with solar energy conversion, which makes this, again, a really exciting field to be part of. So I think now that we got an idea of our three types of processes that can that the light from the sun, the shortwave light, can drive: an optoelectronic process, an optocaloric process, and a photoelectrochemical process. We can then think of those subsystems: the aperture, the receiver, the storage system, the control mechanism, and the distribution mechanism. And now we can get to the core fundamentals of today's lecture. And it starts out with the rules, okay? So light, fundamentally, light is directional. You got to know that. You got to think that way. You got to start to think that way. Light is always coming from somewhere and being absorbed or reflected someplace else. And it has a directionality. It has a storyline. It has a life that is a birth, a life, and a death. And it's a fantastic story that we could bring in. But it also has a language to go with that directionality. So when I write down very specific words here, I need you to take that down for notes. Light is directional, and the language of light is directional. So when a surface is emitting light, when something is glowing light out, and it emits it outward in almost all directions, so we have a term radiance. And you notice that radiance is ANCE, very important in the future, and it's going to be units of watts. That's going to be energy per second, energy unit per second, energy unit per time, per area, meter squared, per steradian. And that would be that directionality that light can go out in an angle in any number of directions. That's the emitting surface. That's the beginning surface. And then light has a directionality, right? It goes from there to be ultimately absorbed. And the light that is incident on a surface is called irradiance. I-R-A-N-C-E. Pay attention to the I-R. The I-R means the light is being incident upon a surface. And then our units are just watts per meter squared, because it's effectively any flat surface on the surface of Earth or out in space is absorbing light or reflecting light, and that light incident on the surface is called irradiance. So if I were to integrate radiance across a number of angles, I would have radiant excidence, which would be the real balance to irradiance. It's a pretty specific term. And then let's integrate the instantaneous energy flow of radiant excidence and irradiance. Let's integrate that and turn that into an energy term. Rather than being a rate of energy transfer, let's turn it into an energy term in terms of joules or BTUs or any other energy-based term. So you'll see joules going on here. And that time change, that integration into being an energy term, turns the two values into shun, from ANCE, ants, to shun. And it's a very specific language inside of the field. So keep that in mind. So radiation in solar, radiation means light integrated across time in terms of units of equivalent units of joules per meter squared per steradian. Irradiation is the one that we'll use quite often. Irradiation is time integrated energy incident upon a surface. Okay, so irradiance and irradiation are going to be terms that we're going to use quite a bit inside of this class. If you want to look at a quick key for that, I'm going to direct you to figure 3.1 in your reading. And then this is where we get to diagramming light. Okay, it connects both the language, radiance and irradiance, and radiation and irradiation together to ultimately think about life, the lifetime, the life cycle of a photon, of light. So first we have a source, and any source of light I'm going to diagram with a curved line. If the light is emitted from the source, if it is glowing from the source, it will have a value of emittance, epsilon, and we will draw a curved line where that surface should be. Then the light itself can be emitted in two generally distinct bands of light: the shortwave band, which is a straight arrow, and the long wave band, which is going to be a wavy arrow. All conventions in this class, all conventions in the Penn State Solar School of Thought. So to remain consistent with what we're doing here at Penn State, this is our diagrammatic technique. That's going to be the birthplace of a photon. Then, during the lifetime of a photon can either be refracted, right? Refraction of light from optics is where light is effectively it's being transmitted through a substance, but it might be refracted. Many of the ways that we've thought of this is like the slowing down of a photon. Or it could be reflected, and that's where you specifically have a surface reflection happening, a scattering event of light of a photon particle. In the case of refraction, we usually use transmittance values, and in case of reflection, we use reflectance values, and those are the Greek letters tau and rho, respectively. Okay, so transmittance, tau, reflection, rho is the general life cycle part of this. So I've gone through the birth and the life of a photon. Now, how does a photon actually end up becoming extinguished? How does a photon die? And ultimately, it goes into a sink. So if a source is glowing light, then a sink is going to absorb that light. And this is like basic energy transfer from a source to a sink. So we can have two things happening at the surface of any particle, of any surface, of anything. We can have light that is absorbed, right? Alpha for absorbed, and where we would diagram that as kind of like a grounding arrow, as light being absorbed. Or we can have light that is reflected off the surface, in which case you always draw this little straight bounce off the surface. Some of the times when I'm doing reflection off surfaces, I will just draw a straight arrow off the surface to keep the diagram simple. You'll see that in some of my later diagrams. That is meant to be reflected light. And, it's really important here when I have questions for you about diagramming light that you understand the difference between a curved line that is emitting light and a straight line that is actually reflecting light. It's going to make a big difference in how you're graded moving forward in the class for diagramming light. Okay. Now there's my long wave light doing the same thing. Curvy line symbolizing long wave band of light, and same idea. If it is bouncing off the surface, so that is light, that is the fraction of light reflected, versus the grounded symbol for light that is being absorbed, or the quantity of light that's being absorbed. So that's the end of the life cycle of the photon of light, and that could be any type of light. That could be the irradiation or the irradiance that your cup of soup is experiencing inside the microwave. It still experiences these same life cycles, just different type of photon. So all of this being fundamental to energy conversion, and this is all diagramming what would be energetic balance between source and sink, so that we obey the first law of thermodynamics, so that we can couple together sources and sinks and the pumping up of energy inside of our systems using light. Fundamental stuff, really important. Light is directional. All this clearly is emphasizing diagrammatically that light is directional. If you see light up in the sky, you're seeing that light up in the sky because the molecules in the sky are actually helping to scatter that light. That blue wavelength is a scattered wavelength of light that you're seeing with your eyes. But the sky itself, right, the whole dome, we call it the sky dome, that is not the sun, is a source of light. It's just a source of reflected light, diffuse reflected light. Very valuable in solar energy conversion systems, just like the ground is a source of light. Okay, moving on. The other side of things, another rule of light, these are kind of laws of light, is that light is spectral. Light is spectral, meaning that everything glows, and potential exception being dark matter, right? But well outside of our field of expertise. That's okay. But everything that we experience in most of our everyday lives, everything glows. And there is going to be a spectrum, a spread of wavelengths for all surfaces. So if I were to plot wavelengths of energy versus irradiance, remember irradiance is going to be watts per square meter. And only in this case, my plot of irradiance is going to be broken up into steps that are going to be 1 nanometer apart. You're going to see this kind of humpback shape that's going to look a lot like the Maxwell-Boltzmann distribution, only it's not. This is a mapping of what you would see as the Bose-Einstein distribution of energetic states or microstates for light, right? So you'll see that there is going to be a lambda max. There's going to be a wavelength lambda, some nanometer band, that is the maximum irradiance for any surface that's glowing. And again, this is the Bose-Einstein distribution. I highly recommend you to try out hyperphysics. Look up Bose-Einstein and hyperphysics. You get a great background from University of Georgia contributors. And where that lambda max has a relationship, a fundamental relationship that is important to radiative transfer. It's going to be 2,898 times 10 to the 3, 2,898,000 nanometer Kelvin divided by the temperature of whatever surface you're looking at. That will tell you, that is a fundamental relationship that will tell you what lambda max is. All right, so let's take a look at that. How would I find out what lambda max is for the sun, which would be approximately 6,000 degrees Kelvin, versus, say, something at room temperature, like one of our tables in front of us, which is about 300 degrees Kelvin. Okay, really, when we're talking about the difference between 6,000 and 300, we can really round out. Just as a quick reminder, highly recommend you reading in your appendix of the Solar Energy Conversion System book, the appendix on numeracy. You're going to be using tools, numerical tools, say in Scilab, MATLAB, and the like, that will give you insignificant digits. That'll give you values of that where you're out to beyond significant digits, and it's worth knowing what are good practices in that. That's in the appendix of the Solar Energy Conversion System book. Okay, so back to 6,000 versus 300K. A 6,000 degree body is going to be a hot body, and it's going to have that lambda max associated with this dark green curve. It's going to have a much higher area integrated under the curve, versus 300 degrees, which will be the wavelength, the maximum wavelength, will be redshifted to a cooler temperature surface. So redshift means that this side is blue, the right side of the axis moves toward the red in kind of a visual sense. So a redshift is moving to longer wavelengths being lower energy. So I get less energy, so I drop down in intensity. The intensity of the graph drops down, and it shifts out to the right, a redshift. When I compare two surfaces, what are their Bose-Einstein distributions at the surface where it is being emitted? And notice how the lower temperature curve fits within the envelope of the higher temperature curve. The envelope being like this actual curve. This curve fits in the envelope of the bigger curve. And that is very specific to Bose-Einstein distributions. You don't see the same kind of plotting usually when you look at the energy distribution curves of particles, the kinetic energy of particles that you would see in, say, the Bose-Einstein distribution. If you don't know what I'm talking about with Maxwell-Boltzmann versus the Bose-Einstein distribution versus the Fermi-Dirac distribution, again, I highly recommend you do your reading and you look into hyperphysics. These become important tools to be talking about energy and light and why the foundations of this stuff is so important. Okay, so if I have a thermal-ish source of light that is the photosphere, that's that outside portion of the sun, it's called the photosphere, The thermal source, and I call it thermal-ish because there's actually some stimulated emission that occurs at the sun's surface that is more like laser generated light is stimulated emission. So that's a part of this, but for the most part, thermal-ish source of light. So thermal source is a photosphere. It generates this short wave band of light from 250 nanometers to 2,500 nanometers. Again, we try to group these things in ways that are relatively easy to memorize. These are pretty open distributions, but they really tail off between about 250 nanometers in the ultraviolet, way out to 2,500 nanometers in the infrared. Clearly, the infrared is far up beyond the visible band of light. Visible band is anywhere in that range between 380 and 780 nanometers. So shortwave band encompasses the visible band and includes the ultraviolet and the infrared. Oftentimes when I use the photosphere light before it hits the Earth's atmosphere, I can go out to 3,000 nanometers. So then, if my thermal source of a surface source, remember everything glows, so everything has a thermal character to it. It has a temperature to it that is the connection between internal energy and entropy changes. That thermal source, if it's the Earth, if it's the atmosphere, if it's the clouds, if it's trees, if it's an ice cube in your beverage, it's all emitting into the long wave band. And that long wave band is about from 3,000 nanometers out to about 50,000 nanometers. And by that point, you could also convert that to micrometer units. This is where unit conversion becomes important, which would be between 3 and 50 micrometer units. Oftentimes, we're going to be staying in nanometers, but just so you know, there we are. So difference between shortwave band comes in from the sun, and the long wave band, which is basically all the light for everything that's glowing on terrestrial sources of stuff, including clouds, including the sky. We've got two different bands of light. So, and notice that light is spectral. There is going to be a spectrum, a spread of energy states, and different numbers of photons for each one of those energetic states, where the maximum number of photons, effectively, is going to be called lambda max. And it's the most probable wavelength of light that you might be measuring. Now, irradiance is, again, irradiance is that term. That's IR is the term for the light that is received by a surface. We're not presuming that it's reflected or absorbed. It's just light that is received by the surface. Irradiance, and ANCE tells me it's going to be a units of watts per square meter, or power density. Irradiance decreases with distance, and it brings in the next law of light, which is the inverse square law of light. So if I draw for long distances between the sun, between Mercury, between Earth, I can demonstrate the inverse square law of light. So light is going to decay with distance, but because light is being spread out across an entire sphere of area, we have an inverse square relationship. So here we are on Earth. We're 93 million miles away from the surface of the sun. 1 astronomical unit, which would be AU, and that is also 150 million kilometers of light. So we're 150 million kilometers of light away from our favorite fusion reactor. Now, we are 1 astronomical unit across this entire distance, whereas Mercury is about 0.387 astronomical units. Now we can use our relationship here to answer what's the intensity of light between these two surfaces. We're going to introduce a symbol called G, which is going to be for irradiance, G. It describes the kind of an annual instantaneous average irradiance right now. The irradiance at the surface of the sun, okay, at the photosphere. Okay, this is light is only emitted from the surface. There's no light that we're talking about internal to the sun. This is light emitted from the surface of the sun, from the photosphere, and that's going to be 6.33 times 10 to the 7th watts per square meter. That is a lot of energy, folks. A lot of energy. By the time we get to the Earth's surface, we have a G Earth that has been measured as of about the most recent measurements from NASA as being an average annual value of 1,361 watts per square meter. So 1,361 watts per square meter is the irradiance at Earth's surface averaged, hitting the surface of the Earth. This is before the atmosphere. This is before tilt of the Earth changes things. It's just 131.61. We're going to use that value, 13161, in a lot of our calculations. Note that in earlier measurements from a decade or two ago, that value was estimated at 1,367. It is no longer that. It has been corrected. It's 1,361. Okay. Now our approach is just to use a ratio method where G1 over G2 is going to be equal to R squared, because it's an area, over R squared. So note that I've got the two G1 with a reciprocal relationship to R1 squared. Okay. Now I input my 1361 and I input my astronomical units in here, and I find out that the irradiance that I could estimate for the surface of Mercury is going to be about 9,087 watts per square meter, right? So nearly 8 to 9 times the value of what we receive at Earth's surface is going to be the average annual irradiance of Mercury. Significantly higher. It's not a linear relationship, it's an inverse square relationship. So I go from, think about numeracy again, go back to that appendix and read up on numeracy, and you're going to see that if I round from 6 up to 1, I have effectively 10 to the 8th watts per square meter. That goes to 9,000. Let's round that up to 10,000, so that would be 10 to the 5 units of watts per square meter, going down to 1,367, which would be 1,000 watts per square meter. And what we're seeing here is a real non-linear response, right? 10 to the 8th to 10 to the 5th to 10 to the 3rd, all across that distance, right? We go about 30% of the distance and we drop 3 orders of magnitude. We go the full distance and we drop 5 orders of magnitude, right? Orders of magnitude difference, that's not linear, okay? So keep that in mind. You're going to have some problems asking about that, but it's another law of light as we move forward in the class. Moving on with that, one of the ways that you'd look at this, we're going to go back to the Bose-Einstein distribution. We're going to see what happens to the distribution as you go further out in space and distance from the surface of the sun. So let's assume that 5,777 Kelvin surface. The lambda max for that, if I were to run the 2898 times 10 to the 3rd Kelvin nanometers divided by the temperature, I'd get a lambda max of 500 nanometers, which is about a little bit blue-green. It's a little greener than the green that we'd find in our green lasers, which is about 550 nanometers. It's definitely different than the red lasers that we have, which are about 650 nanometers in wavelength of light. So there's that lambda max, and you use that lambda max to kind of gauge where the temperature of the surface emitting is coming from. Something that is from the surface of the Earth is going to be a very different temperature surface and a much longer wavelength of light that is going to be much lower in intensity as a curve goes in the Bose-Einstein distribution. So if I go out in distance, I'm not actually, what we will find is that I'm not actually shoving the peak wavelength down and out to the redshift. I'm actually only having a decrease in the number of photons out there. And so you see this vertical drop. And of course the long tail of that curve is also dropping, but it's dropping so low that it's no longer a significant contributor to what we see at what we'd call air mass zero, or the very surface of the outer atmosphere of Earth. So even though the sun might be emitting long-wave light, we don't actually receive that long-wave light from the sun because of the inverse squared law, because all the density of photons are getting spread across space to the point where the long-wave portion of the light is effectively not a contributing feature in light that is received at Earth's surface. So you see that in that function as a vertical drop of lost energy with distance. We note it as the long wave contribution being lost from the sun. This is where I can really say, right, that anything long wave is coming from the Earth's surface, from the clouds, from the sky, from an ice cube. It's not coming from the sun. Shortwave light is coming from the sun, and there's no redshift. There's no shift of the maximum, of the lambda max, out to the longer wavelengths of light, out to the lower energy wavelengths of light. All right, so coming up on Tuesday, we've covered quite a few things in today's lecture. You are more than welcome to look at the talk that we've got here, pause it, take some notes. This is kind of a benefit of having a video lecture of some core materials, because on Tuesday we're going to review what we just talked about, and we're going to incorporate them into what we call the 4 laws of light. These would be 4 classic laws of light in radiative transfer. Again, remember, light is talking about all wavelengths of electromagnetic radiation. And again, when it's received on the surface, we'd call it irradiance. And we're going to talk about that in detail as the 4 laws of light. So first is going to be Kirchhoff's law of thermal radiation. So you're going to want to read up on Kirchhoff's law of radiation. Wien's displacement law, that is that redshift and downshift of light that was described today. And we are talking about Planck's law. Planck's law being the way that we can break down the Bose-Einstein distribution into energetic contributions by small steps, by wavelengths of light, as well as the Stefan-Boltzmann law. And Stefan-Boltzmann law is a fundamental principle of the energetic potential glowing out of any surface of light. That's Stefan-Boltzmann fundamental physics going on here. Actually, all of this is fundamental physics, but key to our understanding of solar energy conversion systems. Because again, if we go back to the beginning where I was starting, nobody is taught how to be a solar energy scientist and engineer and designer. You are learning that right here. This is the next generation of solar energy. This is the Penn State School of Thought moving forward in solar design and solar science. And so this is quite an exciting time where you are breaking ground, but we're tying together a lot of these things that you've heard before in bits and pieces in physics classes, in thermodynamics classes, in heat transfer classes, and meteorology classes. But we tie them together here to give you the foundation so that you really know your stuff as a practicing engineer, as a practicing finance business person, as a practicing meteorologist who is feeding information into the solar energy institution of businesses and corporations that are coming out and communities that need to make decisions on solar energy risk. You need to know these fundamentals. So, coming up also is going to be diagramming light, graphical analysis of sources and sinks for radiative transfer. We described it a bit today, but we're going to go more into detail. We're going to use it more. Again, diagramming light, fundamental to what we do here at the Penn State School of Thought for solar energy conversion, and very useful as we move forward. So you're going to see it coming up over and over again in my work. In your lectures, right? So I look forward to seeing you all in class, and hope you have a great week. Good day.